All right, today we're going to tackle a real classic, problem 1.37. Now, if you've ever studied physics, you know this problem comes from a book that's, well, let's just say it's legendary for being tough. But don't worry, we're going to break it down together. Let's dive in. Yep, this one's from I.E. Irodov's Problems in General Physics. And if that name gives you flashbacks, you're not alone. It's famous for its super challenging problems. But look, the point here isn't just to race to the answer. We're going to walk through the logic step by step so you really get the physics behind it. Okay, so here's the problem statement. We've got a point. It's moving along a circle, and its velocity is given by v equals a times t, where a is just a constant, 0.50 meters per second squared. Our job? We need to find the total acceleration of this point at a very specific moment, right when it's covered exactly 1/10 of the circle since it started moving. Got it? All right, with any physics problem, especially a tricky one like this, first things first, let's break it down. What do we actually know, and what are we trying to find? Okay, let's take inventory. The problem gives us the velocity function, v equals at. We know the constant a is 0.15 meters per second squared, and we know the fraction of the circle, n, is 0.10. And our goal, our mission, is to find the total acceleration. Let's call it w, just so we don't mix it up with the constant a. Now, before we jump into any calculations, we have to talk about the most crucial concept here. You see, when something's moving in a circle, its acceleration isn't as simple as you might think. It's not just one thing. It actually has two different parts, kind of like two faces of the same coin. First up, we've got something called tangential acceleration. Just like the name says, it's tangent to the circle. It points right along the path of motion. And its only job, its whole purpose in life, is to change the object's speed. The best way to picture this? It's the gas pedal. It makes you speed up or slow down. Okay, so if tangential is the gas pedal, what's the other part? That's the normal acceleration. This one is always pointing straight towards the center of the circle. It's perpendicular, or normal, to the direction you're going. And its job isn't to change your speed, but to change your direction. It's what keeps you turning. So think of it as the steering wheel. It's constantly pulling you into the curve. So there you have it. Tangential acceleration, the gas pedal, changes your speed. Normal acceleration, the steering wheel, changes your direction. They're doing two totally different things, and that's the key. It means we have to figure them out one by one. So how do we get the total acceleration from these two parts? Well, think about it. The tangential part points forward, and the normal part points inward, to the center. They're always at a perfect 90-degree angle to each other. And what does that remind you of? A right triangle. The two components are the sides, and the total acceleration is the hypotenuse. So we can just use the good old Pythagorean theorem to find its size. All right, enough theory. Let's get our hands dirty and start calculating. We'll start with the tangential component, because honestly, it's the easy one. And the problem actually gives us a massive clue for this. Remember? It says velocity, v, equals a times t. And what is tangential acceleration, by definition? It's just how fast the speed is changing. In calculus terms, that's just the derivative of velocity with respect to time, dv over dt. So if we take the derivative of at, we just get a. It's a constant. The tangential acceleration isn't even changing. It's just a, which is 0.50 meters per second squared. And just like that, boom, we've got the first half of our answer. That was almost too easy, right? Okay, one down, one to go. Now for the normal component. And this is where things get a little more interesting. This is the real meat of the problem. So the formula for normal acceleration is v squared divided by r, the radius. Okay, so we need the speed, v, at that exact moment, and we need the radius, r. But hang on a second. Go back and read the problem again. Do you see a radius anywhere? Nope, it's not there. It feels like we're stuck, right? How can we solve this if we're missing a variable?
Well, this is where physics gets really clever. We're not stuck. We just need a good strategy. Here's the plan. First, we're going to relate the distance the particle traveled to that radius r we don't know. Then we'll find a different equation that relates the speed to the distance. And then we're going to put them all together. And you'll see something kind of magical is about to happen.
Okay, step one. The problem tells us we've gone a fraction n of the way around the circle. The full distance around a circle is the circumference, right? 2 pi r. So the distance we've actually traveled, let's call it s, is just that fraction n
times the circumference. Makes sense. S equals n times 2 pi r. Step 2. Now we need to link our speed to that distance. And since we already figured out that the tangential acceleration is just a constant a, we can pull out one of our trusty old kinematics equations. You probably remember this one, v squared equals 2 times a times s. It's a classic for a reason.
All right, now it's time to combine things. We start with our main formula. Normal acceleration is v squared over r. But wait, we just found a new way to write v squared. It's 2as. So let's swap that in. Now our formula looks like normal acceleration equals 2as divided by r. Okay, we got rid of v, but we still have that annoying r that we don't know. But now for the crucial step, the big reveal. Remember what s was from step 1? It was n times 2 pi r. Let's substitute that in for s. So we get 2a over r times n times 2 pi r. And look what happens. We have an r on the bottom and an r on the top. They cancel out. They're gone. That variable we were worried about, the one that wasn't even in the problem, it just disappeared. It turns out we never needed it at all. How cool is that? So after all that, what are we left with? Just a nice, clean formula for the normal acceleration. It simplifies down to 4 times pi times n times a. And the best part? We know every single one of those values. We're finally free of all the unknowns. And there we go. That was the hard part. We have our tangential component, and now we have our normal component. We are on the home stretch now. All we have to do is put them back together. So let's go back to our Pythagorean theorem. The total acceleration w is the square root of the tangential part squared plus the normal part squared. We plug in a for the tangential part in our new expression, 4 pi na, for the normal part. We can clean this up a little bit by factoring out the a, and what we're left with is this final equation right here. And from here, it's just plugging in the numbers. We know a is 0.50, we know n is 0.10. Punch that into a calculator, and we get our answer. The total acceleration at that moment is about 0.8 meters per second squared. And that's it. We solved it. Great job. But hey, before you go, let me leave you with a little food for thought to make sure this really sticks. In our problem, the particle was speeding up, right? So what if it was moving at a constant speed instead? Think about our two components, the gas pedal and the steering wheel. If the speed isn't changing, which one of those would have to be 0? And what would that tell you about the total acceleration? Mull that over. If you get it, you've absolutely nailed this. Thanks for sticking with me on this one.